We are going to talk about one-dimensional kinematics, and kinematics is the study of motion. It is actually describing motion. There are two parts to the study of motion. There's kinematics, describing motion, and there's dynamics, which is looking at the causes of the changes in motion. When you combine these two, you get mechanics, what is known as classical mechanics. We'll get to that later. But let's describe motion. We could describe motion with speed, velocity, acceleration. There's also the concept of the jolt. The difference between these is simple. Speed is just distance over time. Velocity, it's like speed, but it's adding direction. And it's defined as displacement over time. And we'll talk about displacement in a minute. Acceleration is how the velocity changes with time. And then the jolt or the jerk is how the acceleration changes with time. So we're taking these rates. And when we go from velocity to acceleration, it's a rate of a rate. And from acceleration, it's a rate of a rate of a rate. And that's why the units have more than 1 second in them. If you look at velocity, its units are meters per second. Acceleration, the units are meters per second, or meters per second squared. The jolt, you would have meters per second squared per second, or you could say it as meters per second cubed. And I know that sounds strange. Now, when we talk about motion, we're talking about a change in position relative to a reference frame. Now, our most common reference frame is the Earth with synchronized clocks. We do say all motion is relative because it's relative to this reference frame. We have to choose our reference frame first before we start asking questions about motion. You need to pick your reference frame. For right now, we're going to choose the Earth with synchronized clocks. It's known that the reference frame we're really interested in is an inertial reference frame, and we're going to treat the Earth with synchronized clocks as a good approximation of an inertial reference frame. It's not technically, and we'll talk about why in class, but for right now, we're going to treat it as an inertial reference frame. It's pretty good for what we want to do. Now, speed is the first physics model you're going to learn, and you already know it from driving. It's what you are familiar with your speedometer in your car. Your speedometer in your car will measure your instantaneous speed. We're going to calculate averages for the most part, but you can have constant speed, averages, and instantaneous. We're also going to be graphing this information on what are called position time graphs. We're going to do velocity time graphs. We'll even do acceleration and time graphs and such. But position and time graphs is what we usually start off with. The graph is called a world line because it's the history of the position of an object at all points in time. You could actually create one of these for yourself, and it would be your history. We'll study this in detail. So the motion concepts. The first thing you need to know is position is usually given the variable x, like the number line, the x number line, the x-axis. In your book, x is also called the instantaneous position. We're just going to call it position for short. It's where an object is relative to some origin. You do have to pick an origin. We label the origin 0 for its position. We use 0 to mean a position on a scale, on a number line in this case. This choice of origin is arbitrary. In one dimension, we will have a positive direction, we will have a negative direction, and of course, it'll be all relative to the origin. And we're going to focus on motion in one dimension at this point. So imagine, everything moving along a straight line, and we'll indicate direction by the sign, well, the positive direction and the negative direction. So displacement will be a change in position. You have a starting point and an ending point, and we will label that starting point typically with x sub 1, and that ending point typically with x sub 2. In your book, they use f's and i's for final minus initial positions. What I have here is our change in position, and I'm using the Greek letter delta for change in. Change in x is change in position. we would say it equals the final position minus the initial position. Mathematically, we would say x sub 2 minus x sub 1. There's many different ways to write this, but remember, it's just a change in position. You have a starting point and an ending point. And if you're on a number line, mathematically, it's the difference between those two. And remember, this is a subtraction sign here, and it means add the opposite. You will have to add positive and negative numbers. So displacement can come out positive, negative, or 0, and the sign will give its direction. It's actually a vector quantity. It's different from distance. Distance is just how much ground an object actually covers. It's always positive. It always increases your distance. It doesn't matter if you backtrack. It just keeps adding and keeps adding. It's what is shown in your car. If you go get your oil change, they'll look at your mileage and they'll add 3,000 miles to it, maybe 3,000 to 5,000 miles to your mileage. So as a reminder to come back and get your oil changed again. Here are some more motion concepts. We have displacement, and I have the formulas below here. There's different ways to write it. Remember, displacement is change in position. Endpoints alone matter. The details of the motion between the endpoints are irrelevant. You just need to know where you start and where you end. What's interesting, if you start and end on the same point, it doesn't matter how much distance you covered, your displacement is 0. So be careful with displacement because it can be positive, it can be negative, it can be 0. And it's because of how it's defined and using the subtraction symbol, which means add the opposite, so you will be adding positive and negative numbers. This can work out to be 0. So here's the way your book writes it. Delta x, or change in x, your displacement, will equal your final position minus your initial position, or xf minus xi, or you could say it x sub f minus x sub I. It's best to put it in words, though. Your displacement equals your final position, which will be a number with a dimension like 5 meters, minus your initial position, which could be a number and a dimension like 2 meters. So 5 meters minus 2 meters. What would your displacement be? 3 meters, but it would be a positive displacement. You could write it this way, x sub 2 minus x sub 1, or x2 minus x1, like you do in math class when you're figuring out slope. You'll find the change in the x position or the x-axis, the horizontal. It'll look like this. That should look familiar. I like to write it x minus x sub 0 or x naught. Another way to say that. That's when you start your timer at t equals 0 when you're at position, the initial position. You can always treat your initial position as the origin, where you start. And your final position could just be called x. So you might see me write it this way, x minus x naught. But these all mean the same thing, your final position minus your initial position. And we can represent displacement with a vector. We could represent it with an arrow, where the length of the arrow is the magnitude of the displacement, like 5 meters, a numerical part with a dimension, that's magnitude. And the direction the arrow points, well, that's going to show the direction, magnitude and direction, that's a vector. Distance now. Distance is a scalar. It's just a positive number. But displacement is more than that. It's magnitude and direction. You have to add the direction. That's the big difference between the two. They're different mathematical quantities too. They follow different mathematical rules. Here's a position versus time graph. There's a world line on here. The yellow means that this has already occurred. So if you imagine this motion happening on a straight line, that a person could have walked, let's say 1.2 kilometers. You read the axes here, 1.2 kilometers or 1,200 meters. Remember, K stands for 1,000, so multiply 1.2 by 1,000 or 10 to the third power. You could write this as 1.2 times 10 to the third meters and move the decimal over 3, so 1,200 meters. You're walking along this path here, walking up 1.2 meters. Then this means you're at the same position as time passes, so you're at rest. And then you continue back. You go, let's see, 0.2, 0.4. Yeah, so 1.8 here. Is that right? Looks right. So you're backtracking, and then if you rest a little bit more, and then you backtrack all the way back to the beginning. So if I asked you what your displacement would be, it would be 0, because you went this way, and then you came back. You went 1.2 kilometers in the positive direction, and 1.2 kilometers in the negative direction, and you ended up where you started, so your displacement is 0. Your total distance would be 1.2 plus 1.2. You're not moving here, you're just standing there. So you would have 2.4, or so 2,400 meters, if that's correct. That looks correct. Now this time is in minutes. If you want to convert these into seconds, you'd have to multiply by 60, because 60 seconds per minute. So be careful with the axes here. If you wanted to answer your questions in meters or meters per second, you would have to do some conversions here. So speed, distance per time, always a positive quantity. Direction of motion is irrelevant. May vary depending on time interval. Velocity, which is related to speed, but it's not distance over time, it's displacement per unit time. So you'll see this change in x. Remember, change in x is displacement, and change in t is your time interval. Change in x over change in t. This slash mark is division, so displacement divided by time. All that matters when you're talking about velocity, and this would be average velocity, is the displacement and the time interval. The details of the motion are irrelevant. Lots of things could happen. When you're talking about averages, you're not getting all the details. You're trying to get a good measure of the motion, and usually it is a good measure of the motion, but there's some things you need to watch out for, and I'll show you those. It can be positive or negative. It also can be 0. There could be no change, or the velocity is just 0. There's no change in position over time. However, with averages, you could have moved. You just returned to your initial position. You have to be careful with this. This may vary depending on the time interval. Obviously, if you make this time interval very, 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 very small, you get closer and closer to what's called the instantaneous velocity. Oh, here's another graph. The yellow is you moved at a constant uniform speed, uniform velocity, which works out to be 1 meter per second. The way to figure that out is take this distance, 1.2 kilometers. Remember to multiply by 1,000, 1,200 meters, and divide it by the time interval. If it's from 0 to 20, you'd multiply 20 by 60. That's also 1,200 seconds. So 1,200 meters divided by 1,200 seconds, you get 1 meter per second. Now the velocity, you also get 1 meter per second. The reason it's positive is because you're moving in the positive direction. You have a positive slope. If you figure out the slope of this line, it is the velocity, the average velocity, because that's what slope is. It's a change in this axis, the y-axis, which happens to be the change in position, over the change in the x-axis. In this case, it's time, so over change in time. So the change of the vertical quantity over the change in the horizontal quantity will give you this slope, which we're going to call the velocity. It has physical meaning. Now, speed is always a positive number. Okay, we look at this segment. Now, this slope is the negative of this slope. It's still a constant rate. It's going to still be 1 when you work out the numbers. But notice it's negative. You're backtracking here. And then for this trip, if we compare average speed to average velocity, the question is, will we get the same answer? And the answer is no, because with distance, the distance is adding up. But with the displacement, you're backtracking. You're going up to 1.2 kilometers. Then you're coming back to this location. So you went, if you multiply 0.6 by 1,000, you got 600 meters. You're only 600 meters in the positive direction away from the origin. It's still a positive displacement, so it'd still be a positive average velocity, but you backtrack. So the numbers should not be the same. Let's look at those numbers. Distance, 1.8 kilometers. The total travel, you went up to here and you came back. Yeah, that's 1.8. The speed, you would change kilometers to meters by multiplying by 1,000. the time, you got to change this time interval to seconds by multiplying by 60. You get 0.86 meters per second. However, if you were to take the displacement, which is plus 600 meters, and put it in here, you would not get the same answer because that's less than 1,800 meters you backtrack. So let's see what that is. Well, you put the 600 in there over the time, you get 0.29. So these are different. So it's not true that speed and velocity, when we're talking about averages, are always the same number. You have to be careful with this. It depends on the question. It depends on if you're talking about instantaneous velocity and the magnitude of instantaneous velocity. Magnitude of instantaneous velocity can be the speed, but we're talking about averages here, and averages don't include all the detail. So the magnitude of the instantaneous velocity is the instantaneous speed, at that particular point. If you look at this graph, we're looking at points across time, and we're not getting all the details of the motion. Still useful, though. In physics, we will talk about the particle model. We're going to treat all objects as point particles. We're going to call it the center of mass. You'll find a concept called the center of mass as if all the mass of the object is concentrated at that point. We'll talk about that. Sometimes it's called the center of gravity, but they're not necessarily the same point. For them to be the same point, the object has to be in a uniform gravitational field. We'll talk more about that later. And these are known as free body diagrams. When we get rid of the object and we just replace it with a point particle, it becomes a free body diagram. You don't have to be a great artist in this course to draw a car or anything. You can represent the car with a dot, and we're going to do that. It simplifies things. Plus, it's neat. It works. So once again, distance, total length traveled, displacement, change in position, delta x equals, change in x equals x minus x naught, or you could write it as the final position minus the initial position. Takes getting used to, I know. The average speed, distance, or the total distance over the total time taken, the elapsed time. The average velocity, again, displacement divided by the time. And it's the average velocity. We could write it as v sub average. You can say it this way, delta x over delta t, because we're using Greek letter delta for the change, the triangle, change in x over change in t. Or you could say change in position over change in time. Sometimes we just put t down here for time because one of the times is 0. We start our stopwatch at t equals 0. So we're just using the final time. There are ways of, simplifying this. And here's another way to write average. You write v and you put a bar over the top, and it means v average. You might see that written. It just means the average velocity. All of this here is the way to calculate it mathematically. This expression, change in x over change in t, or displacement over time, if you have a position versus time graph, you can find the slope between any 2 points. And by finding the slope, as you do in your math classes, you can figure out the average velocity graphically, and we will be doing that. So here's some more information about this. The values for average velocity, again, it can be positive, negative, or 0. You can think of it as speed and direction. And if you have a graph of it, graph of position versus time, it's the slope of that line is the average velocity. I really should have a bar over this v or put a subscript v average. But it's understood if these are deltas that this is the average. Here's a graph of position versus time. If you pick 2 times, figure out the slope between those points. Remember, slope is change in the vertical, the change in the y over the change in x. In our case, x is going to represent position. I know it's on the y-axis, but it doesn't matter what you put on here. X in our case means position, so change in position, which is displacement, over change in time, it'll be the slope of that line, just like in your math classes. But the slope of the line has meaning. It's the average velocity. So position versus time graph, remember it's called a world line. The average velocity is the slope of the line between any 2 points on the graph. That angle there, remember angles, if they're clockwise angles from a terminal side, this dotted line here would be the terminal side. Clockwise angles are negative, going this way. Counterclockwise angles are positive. So that's a counterclockwise angle there. It's positive. And the slope is positive. We look at that angle. Velocity is sign sensitive. Velocity is sign sensitive. Here's a graph of position versus time. The average velocity is, you're trying to figure it out by finding a point on, this is the motion of the graph, right? Or the motion is represented by this, looks like a purple graph. Pick a point at some time t1 and some later time t2, draw a line between those 2 points, find the slope, and that is the average velocity, whatever the slope is. It doesn't include all this detail of the motion, though. If you want more detail, you move these. Like if you want to know the exact velocity right at this point, you need to move this point closer and closer and closer, or make this line steeper and steeper and steeper. What you're doing is making this time interval very, very small. And the closer you get it to 0, though we can't divide by 0, but we can approach 0, you'll notice that this line will just kiss the curve, and it's known as a tangent line at that point. If you find the slope of that, you find the instantaneous velocity at, say, t1. Let me just show you what that looks like graphically. Here we are. If we look closely at it and zoom up, move those t's closer together, make that time interval small, it'll look something like this. And notice how this line is just kissing the curve. If I keep doing this, it's going to kiss the curve right at t1. Then I find the slope of this line, just like in your math classes, and I have the average velocity. Or not the average velocity, sorry, the instantaneous velocity. Right now, if I go back, this would be average between these 2 points, but it's getting very close to instantaneous at t1, even at t2. So the further they're apart, the less detail you get of the motion at any particular point. So bring the points together, draw a tangent line. Now I didn't draw the tangent line in here, but it should just kiss this curve right here. And if I figure out the slope of that, it would be the instantaneous velocity at t1. So notice the difference between this and this. This is average. Over here, I'd have a line. I didn't draw it in. I'd get instantaneous velocity. So we say it's the limit as our time interval gets very, 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 very small. And I think that's it for now. Enjoy.